Hey guys, in this video we're going to be trying to find the eigenenergies and eigenfunctions of a quantum particle in an infinite square well. Hence we're basically trying to solve the particle in a box problem, but we're only going to do it for one dimension. Okay? So the way we have to think about this is pretty much, well, to solve this problem here, since it's a quantum particle, we need to basically use the Schrodinger equation. Now, since it's only one dimensional, we only have to consider one direction. So the Schrodinger equation is written as follows. So it's negative h bar squared over 2m, partial derivative, the second partial derivative with respect to the wave function, the second partial derivative of the wave function with respect to its position. Now it's only one dimensional, so we only have to consider x, we don't have to consider y or z. Plus the particle's potential. So I'm just going to say v of x, or you can write it, it's written as u of x sometimes, multiplied by the wave function, is equal to the energy multiplied by the wave function. Okay? Now, what is this actual problem? So the infinite square well problem basically means we're having a particle that can move left and right. So it's pretty much set up like this. So you can draw your diagram like this. And let's just say it's like this. So it's going from like 0 to some place A, okay? Now, the way we have to set this up is pretty much, we have to think about things in physics. So if you've heard of a potential, you know that things in the universe tend to go towards a lower potential. So for example, electric potential, gravitational potential. So that's the same here. So the way we've got to set this up is basically saying, alright, if things go towards a lower potential, and we only want to know that the particle is within some certain box, so it can only move left and right, we basically say that its potential in here is going to be 0. Now, we're also going to say the potential on the outside is going to be infinity. So the reason we're saying it's infinity, because objects like to go towards a lower potential, by saying the potential is infinity outside the box and on the box walls, let's say, then it's basically saying, alright, the particle isn't out here. And since it's a quantum particle, we have to treat it as like quantized, hence we have to use the Schrodinger equation to find it, okay? Okay? So let's just have some conditions here. So yeah, the potential on the inside of the well is 0, and the potential on the outside and at the walls is infinity. Now, what this basically means is, alright, the particle's not out here. So the probability that the particle is out here is 0. Hence the wave function outside here is 0. So, right, omega of x is 0 here. So it's 0 outside here. And we want to find pretty much the wave function on the inside here. Because if we're trying to solve for the eigenenergies and the eigenfunctions of a quantum particle in infinite square well, we gotta find our wave function, okay? Because our wave function basically tells us all about the particle, because in quantum mechanics things aren't deterministic, they're probabilistic. So you don't know exactly where something is, you only know the probability where something is, okay? So this is why it's so important we've got to set up these conditions correctly, okay? So our potential for our quantum particle is as follows. So it's pretty much 0, where x belongs between 0 and a, and it's infinity elsewhere. Hopefully that all makes sense. Now, so these are also our initial conditions here. So what we're saying here is pretty much at this wall here, we're also saying that the wave function of 0 when x equals 0 is also 0, okay? And we're also saying the wave function when x equals a is also 0, okay? So these are also our initial conditions. So we're saying our wave function is going to be, well, it's going to be 0 when, well, we can just leave it like that. We don't have to write it like this. Okay, so let's get solving this equation straight away. So now don't be confused. This here isn't Planck's constant. This is Planck's constant divided by 2 pi, I believe. No, I'm not fully sure off the top of my head, but I know that's not Planck's constant because it's got the bar. If it was Planck's constant, it wouldn't have the bar. Okay, so the reason we can solve this now is because, alright, if we're solving for just inside this well here, then we know that this term here must be 0. So hence, when we're solving our Schrodinger equation, it can turn into a partial differential equation quite easily. So all I'm going to do is move this over to the side real quick. And we know, alright, if it's in the well, then v of x is 0. So our new equation is negative h bar squared over twice the mass, the partial derivative of the wave function with respect to the x position. Now we're using the time independent equation here, we're not accounting for the time at all. And this is 0, so that whole term goes bye-bye. So this is going to be equal to the energy multiplied by the wave function. Okay. Now, to make this easier to solve, we want to get pretty much the derivative by itself. Okay. So the way we do that is we're going to divide by negative h bar all squared over twice the mass. So divide by that, we'll have the partial derivative of the wave function with respect to its position is equal to negative 2m e over h bar all squared of the wave function. Now what we're going to do is make a substitution, because can you agree that this here is basically going to be a constant? Because we can treat it as a constant for now. So we're going to let it like equal k. So let, actually to make this even better, we're going to let k equal the square root of 2me over h bar. Now the reason I'm saying that is because then k squared is going to be 2me over h bar all squared. Does that make sense? Hopefully it does. Alright, so then we can simplify this. So our partial derivative of the wave function with respect to the position is negative k squared of our wave function. Now, what we have here isn't really a physics problem now. It's a math problem. So you can see this is a partial differential equation. So it deals with a second derivative. So we're looking for a function such that if you differentiate it twice, you're going to get negative k squared. So what can we think of functions that cycle itself, that don't disintegrate when you differentiate them? Well, we've got Eulers and we've got sine curves. Now since it's a wave function, I'm assuming it's going to be like a sine curve or cos curve. So if we differentiate sine, well sine x, if we differentiate that, that's going to give you cos x, isn't it? And if you differentiate that again, it's going to give you negative sine x. So if we differentiate it twice, we get the negative of that function. This is looking promising as well. But it doesn't just have to be sine, it can also be cos. Because if you differentiate cos, it's going to give you negative sine x. And if you differentiate that again, that's going to give you negative cos x. Now, we've also got to account for this k squared here. So if you differentiate something like this, so sine of a, if you differentiate that, then the a is going to come out the front. Now, we want a k squared out the front when we differentiate twice. So if we made our function like this, so our trig curve, let's just remove all this for now, and let's really think about like if this can work for our PDE. So if we had, let's say, sine of kx, if you differentiate that, that's going to give you k sine of kx. And if you differentiate that again, that's going to get, oh, that's sine, sorry, that's going to be cos. Cos x, cos. And if you differentiate that again, it's going to be negative, bring the k at the front again, negative k squared cos of kx. This would work for our, oh, that's sine, sorry, I don't know why I keep writing cos. I'm not in the right state of mind for this at the moment. Right, and that works for our equation. Now, we can account for cos as well, and there also could be a constant out the front here, so we're just going to say this is like, I don't know, b. So let's see if this is a solution to our differential equation here. So if we have the wave function, let's just say, alright, the wave function takes on this form, where it's say, alright, a cos of kx plus b sine of kx. Now the reason we've got a and b here, a and b are just constants, because we've got to account for any constants at the front, okay? So let's see if this works. If we differentiate this, so our first derivative is going to be, bring the k at the front, that's going to turn into negative k a sine of kx. Differentiate this bit, it's going to be kb cos of kx. Differentiate this whole thing again. So the second derivative of the wave function with respect to the position. Differentiate this, it's going to be negative cos squared, negative k squared a cos of kx, plus differentiate this, is going to be negative because cos goes to negative sign, negative k squared b sine of kx. Okay? Now you can see you can take out a factor of negative k squared. And what we have here is our original function multiplied by negative kx squared, which satisfies our differential equation. So if you were to plug this whole thing here into here, and this bit into here, it would satisfy the equation. The left hand side will equal the right hand side. Okay, so now we've got a solution to our, well, we know what our wave function looks like, but we've got some initial conditions. So now we're going to go back to the physics of it. So this is good for a math equation, but now we have to think about the physics of it, okay? So we know that the potential energy is going to be 0 in here. We also know at these walls, oh, what did I do? Rub that out. We also know at these walls, when the position is 0, the wave function is going to be 0. So if we put in omega of 0, that has to be 0. So we put 0 into here and here. So what we get is, alright, so therefore 0 is equal to cos, so this is going to be 0 times k, which is 0. Cos of 0 is going to be 1, so a plus b sine of 0. Sine of 0 is 0, and then 0 times b is 0, so we get this. So therefore a needs to be 0. So therefore our wave function has already simplified. We don't have a cos term, we have just this. So our wave function looks just like our sine curve at the moment. Now, we've also got another initial condition. When the wave function is a, it also has to be equal to 0. So omega of a is also equal to 0. So if we put this in, so 0 equals b sine of k of a. Now, b cannot be equal to 0. The reason for this is because, while it would work mathematically, then there would be no particle, because then there'd be no wave function, which doesn't work. However, we do know that this is going to be 0, because it needs to satisfy this. So we know that this bit cannot be 0, so b cannot be 0, but this whole bit has to be equal to 0. So in order for this to be true, then k of a must be equal to a discrete multiple of pi. Because if you put sine of pi, sine of 2 pi, sine of 3 pi, that will be equal to 0. So Ka is effectively equal to n pi, where n is a discrete number. So this is where the quantization, discrete quantization comes in, quantum mechanics. So we've got this set up. So therefore our K is going to be n pi over a. Okay? Righto. Now this helps us a bit. So what we're going to do now is to pretty much work out what our variable is at the front. We've got to pretty much account for the other part of it. So we've solved for the Schrodinger equation, but we also know that this is a probability density function. If you square the wave function, well, not square it, we know that the integral from over the bound is going to be a probability density function. So from 0 to a, we know that wave function dash, so this dash means like the modulus, but since there's no imaginary part, effectively we have the wave function times the wave function, so the wave function squared, the modulus or squared, or you can just write like this, dx is going to be equal to 1. Now, it would have an if we were using the other equation where it counts for time, we'd have an imaginary part, so we'd have to account for the modulus one. But since we don't have one, it's basically the wave function all squared is going to be equal to 1 over this bound here. Okay? So the reason why this helps us is because if we solve this, we can probably find an expression for our constant b at the front here, because we've come into a roadblock down here. So effectively, all we've got to do is put in our equation at the moment. So our equation, our wave function, is going to be, what was it? B sine of Ka. Okay. Now what we're going to do is square this and integrate it. So from 0 to a, if we square this, we're going to have b squared sine squared of Ka dx is equal to 1. Now this is another math problem. So what we can do here to make this simplified is pretty much we know this is going to be a constant, so we can take it outside the integral. So we have b squared, the integral from 0 to a, of sine squared of ka dx must be equal to 1. Okay, so we know how to integrate sine squared kx because there's a little trig identity that if you have sine of, let's say, what was it, sine squared of a, that's going to be equal to 1/2 minus 1/2 cos of 2a. Okay, so this is a little trig identity that comes up in math all the time. Now, which side is easier to integrate, this or this? This side is, because all you got to do is break it up into a couple integrals and then evaluate it. So all we're going to do is replace it in here. So therefore sine squared of ka is going to be equal to 1/2 minus 1/2 multiplied by cos and then double the inside term, so 2ka. Okay, now this is much easier to solve now. So let's just put that in here. So we have b squared, we'll have brackets, and we'll break this up into two integrals, is equal to the integral from, actually we can leave that as one. We'll just leave the b out the front. b squared from 0 to a of 1/2 minus 1/2 cos of 2ax dx is equal to 1. Now we can integrate this, okay? So if we integrate this, we're going to have b squared, and we'll substitute the terms in a bit, so we'll put brackets here. Integrate this is just going to give you x over 2 minus, if you integrate this, you got to divide by the differential of this. So the differential of, what did we do? Whoops, sorry, I made a mistake up here. This isn't a, this is going to be x. Substituted the wrong thing. So that's going to be x, that's going to be x. Therefore, this is going to be x. That's going to be x, because I was thinking, where's our variable gone? X. So then we have to divide by a differential. So the differential of this bit here is going to be, it's going to be -1. I'll just leave the 1 out the way. We can just write, so if we integrate cos, if you integrate that goes to sine, so it's still going to be negative, so it's going to be sine of 2kx over, divide by the differential, so we're going to have 4k on the bottom, and then we have the bounds 0 and a. This is all going to be equal to 1. Now, if you substitute a in, you're going to be left with this expression here, b squared multiplied by a over 2 minus sine of, put the a in there, so 2k of a all over 4k. Now if you put the 0 into here, that's going to turn to 0, and that's also going to turn to 0, because sine of 0 is, 0. So that's going to be 0. So what we're left with effectively is just this here, is equal to 1. So, and we also know that Ka is also going to be equal to n pi, where n is a discrete number. So we can effectively make that substitution in a sec once we pretty much know this. So since we know this, we know no matter what this is going to be, it's going to be 0, because effectively k of a is a discrete multiple of pi. So sine of any multiple of pi that's discrete is going to be 0. So this term effectively is 0. So all we're left with really is b squared multiplied by a on 2 is going to be equal to 1. So therefore, if we rearrange this, we multiply both sides by 2, we're left with b squared of a is equal to 2. Divide by the a, and then square root it. So we'll have 2 over a, square root that, gets rid of squared. So therefore b is going to be the square root of 2 over a. Now, this is our constant in terms of our initial condition up here. So effectively, we've got pretty much a proper wave function. Now you can use this wave function here to find the eigenenergies as well. So we know our wave function, wave of x, is going to be our constant, the square root of 2 over a, sine of kx dx, where we know that k, what did we say k was before? The square root of 2, what was it, 2, square root of 2, and me over h bar, okay? So effectively, what we have here is pretty much, alright, we've got some quantization in here. So this is our general wave function. So if you wanted to find the general expression, so you want the wave function at different energy levels, all we got to do is pretty much substitute in here. Because, alright, we know that this k here, we know that k is also going to be equal to, since we know ka is n of pi, we also know that k is just going to be n of pi over a. So effectively we have n pi over a is equal to the square root of 2me over h bar. And if you wanted to rearrange that for the energy, you could get the energy of n is going to be pretty much h bar all squared of pi a over n. Oh, whoops, that's the other way around. Let's go n over a all squared. Sorry, I'm doing this in my head. So, and then 2m. So our energy, let's sort of rub that out real quick. Our energy is effectively this. So this n here gives you the energy at discrete levels. So effectively, we've got a generalization for our wave function. A wave of n of x is pretty much going to be, let's move this over here, square root of 2 over a sine of k, and I'll put a little subscript n here because we know that can change. Okay. Why did I put the dx down here? I don't need that anymore. So yeah, righto, that's about it. So if you want to find pretty much the energies and wave function at different energy levels, all you got to put in is n equals 1, 2, 3 into here. That'll give you the energy, and this will give you the wave function at those energy levels as well. So the wave function must be continuous over its domain, so it must be normalized. So therefore, we know that the wave functions of 1, wave 2, and wave 3, they must be orthogonal then, okay? So the different n values corresponds to a different wave function with a different energy level. So each, yeah, that's about it. Righto, I don't think we've missed anything or made any mistakes. I wasn't very prepared for this video, but we did pretty good. Alright, if you have any questions, please leave some in the comments and I'll try my best to answer them. Alright, thank you.